I think we can start. Hi, everyone, and welcome to our today's session organized by QFE Theory community. My name is Daria, and I'm so happy to see you all here. Today, we continue exploring the world of artificial intelligence and machine learning. Previously, we had a session where we covered the IS2QB-based theoretical material. The recording of that session can be found on our VIA community platform, as well as our YouTube channel. Today, we will dive deep into practical testing methods of AI solutions. We will learn how to ensure your AI is fair, unbiased, and delivers accurate results. We will cover dataset testing, model evaluation metrics, explainable AI, and ongoing model monitoring techniques. Now, I would like to introduce you our speaker, Victor, a lead software test automation engineer. Hi, Victor.
Hello, everyone. Hello, Daria.
Yeah, before we get started, I want to highlight that if you have any questions about our today's topic, don't hesitate to post them in our chat. In the end, we will have Q&A session and we'll answer all of your questions. Yeah, let's get started. Victor, the stage is yours.
Thank you. Hi, everyone. And today we are going to talk about testing AI solution. This is part 2. And a month ago, we had part 1, where we discussed some theoretical questions about ML, AI, and testing. And if you feel uncomfortable with today's topic, like especially with some theories, some definitions, some procedure of how AI is trained, please refresh your knowledge watching part 1, where Sylvia explained everything in very detail and good manner. But today we're going to talk about more practical stuff, and I'm your speaker. My name is Victor, and I'm lead test automation engineer, as Daria told you. And I have worked with different AI and machine learning project for a couple of years now. And today I would try to share my knowledge, best practices, and a little of pain when we training and testing artificial intelligence, machine learning solutions. Let's start from our agenda. I will try hard to keep this agenda in my mind and not getting distracted or over enthusiastic about some topics. And I will try to cover everything, but it would be hard because there are a lot to talk about, and AI world is deeply involving, changing every day, and new ML models came to real world every day, and testing involves as well, and it became more sophisticated. We get more methods to test different AI. But to be honest, that even testing of AI is in early stages, and sometimes there is no correct answer how to train one machine learning model. There are some best practices, but it doesn't mean that this is end truth. And every project is unique, and for your project, you must know at least how machine learning works and how testing works, and you should learn new stuff from best practices. And today we're going to talk about dataset testing. What does it mean to prepare data for your machine learning model? How to train it in best way, and what problems may arise in the real world when you prepare data for your machine learning model. So this is phase 1, when you gather data and you trying to answer the question, are you doing right? Are you going to train the correct model on correct data? And this is question should be answered before you're going to phase 2, because phase 2 is all about training. And on phase 2, you spend a lot of resources, a lot of money, a lot of computational power, and a lot of electricity bills. After training your model, you're trying to answer another question. Question 2 of our today's session is, do you have a correct model? Have you trained a correct model, a good quality model? And we'll talk a little bit about metrics, how to measure the quality of your model, how to answer the question, how good your model or bad your model. And on this phase 2, you're trying to predict how your model will behave in the real world, in production. And then you push to prod, yes, and you're starting to monitor the quality of your model on production and how good your model in the real world. And there are also can be problems because even the best model, as time passes, it can become obsolete, it can degrade in performance, and in couple of months, years, or even days, you can end up with very garbage model. This is precisely the moment when a lot of machine learning projects fail, because they show a good numbers on phase 2 when we are trying to evaluate the quality of models, but because of lack of monitoring, those models they perform very badly in real world, and user end up dissatisfied with model, and it doesn't work. So we will talk about data shift and concept shift and some model degradation in part 2 of our today's agenda. All right, so let's start without more theoretical knowledge and more talk. Let's start with some practical examples. Will you gather data for your machine learning model? And you have the very old problem, probably as old as testing discipline exists with ambiguous requirements. And you know this pain, and it happened to you before, that you have client, and this client asks you to test your system, but you don't know what is expected from your system, what is correct requirements, what is correct acceptance criteria, and how your system should behave, and what is expected result of your test. And the same applies to gathering data for your machine learning model. You should define very clear and detailed our requirements, how you should label data. If you remember from part 1, basically training of machine learning is showing to the model some examples of data and asking model to predict labels on that data. What is labels? So this is image of cat, and label is cat. This is the image of car, and label is car. But what if you're trying to predict some color of cat, or you're trying to predict that damaged car versus just scratched car versus just good car without any damages. So you don't know, is it on the first picture, is it only scratched, a minor scratch, or is it should be considered as damaged? And on the second image of car, is it completely destroyed car, or is it just heavily damaged car? And the same with colors, the same with different examples of images, of audio, of some text when you're training very popular large language models nowadays. You should know how to label your data, and at first your client should know how to label your data. And it means that you should even consider not just labeling of your data, but condition where your machine learning model would work. Because if you have a lot of pictures of car, and those pictures are made with some camera one, and in the real world, all clients would use different cameras or with different setups, with different color schemes. Your machine learning model will fail in production because it is trained on one type of camera, and it cannot consider all types of cameras with different colors and different resolutions. The same with any data, for example, audio data. You should make sure that very popular technique like to detect background noise on your audio. But what is background noise? Is it like some minor noise, or it any type of noise, and or some different sounds from computer, from microphones? How to correct to label those type of noise? And the same with some transcription on your videos or audios. So right now I'm talking to you, and I am using a lot of E, these just sounds which I make trying to find a correct thought in my brain. And how should you transcribe to transcribe this sound to your label? It's all a very important question. Should you transcript all this ORA in my voice, in my sound, or should you skip it and just leave this text? So all those requirements should be answered before you gathering your data and before you train your model. Yep. So moving on to incorrect data. Let's say that you fixed with your client correct labeling. You know that how to label all data. You know what type of data you need, what condition you would work in, so on. But this is a very important question. Do you trying to answer the correct question, and is your answer what you will get from your machine learning model? Is it helping to business needs of client? So there is a very famous example with incorrect data. So let's say that we trying to train our machine learning model to detect a healthy skin versus, or beautiful skin in this example, versus unhealthy skin. And if you type this beautiful skin in Google, so it will show you a bunch of women touching their faces, some like mostly young women. And if you gather this data and you feed to your machine learning model, this model will not learn how to detect beautiful skin, healthy skin. It will decide that beautiful skin means that women touching their faces and nothing else. So it's we're trying to, with incorrect data, we're trying to answer incorrect question. Basically, we try our model will answer, does this woman touching her face or not, and nothing else. So this is incorrect data. You should gather correct data, and you should come up with all possible scenarios. What your how it's like kid, yeah? How do you teach kid to detect healthy skin versus unhealthy skin? And when I when I compare model with kid, you should understand that machine learning model is a kind of lazy one, because it's trying to simplify its own work. And what I mean that if you show the some incorrect data, it will learn some middle way how to find answer very fast and sometimes incorrectly. And you will ask your model to detect healthy skin versus unhealthy skin, and your model is lazy. Your model don't want to understand what healthy skin means. Your model will just look into if face and hand is close or not close enough, and it will decide that, okay, now I know what is a healthy skin. So you should always keep in mind that your model sometimes will learn not what you want, and ask yourself, does our model learns what we want? Does we gather correct data for this business need? And does our model answer the correct question? Yeah. Another problem, and on part one, we talk a little bit about that problem, is bias in data. And we humans, we are biased. We tend to think about real life, about people, about different things based on our experience. And from all stories that back to like hundreds years ago, when European people they lived in Europe, they never thought that Sven can be black. So all Sven were white in our imagination. And only after European people traveled to different continents, they discovered that Sven could be black. So this is bias, and when we human we gather data for our machine learning model, we transfer this bias to our model. If we find only white swan and those swan, you see from pictures, all those swan, they surrounded by water. Our lazy machine learning model, it will be lazy enough to know what is swan. The easiest approach to predict the answer for this problem is just to detect, is it water and is it white? And if it's water and it's white, then probably it's swan. Even we know that sometimes we can have images of swan on some land, on soil, and sometimes we can have black swans. So if you were present with us in part one, you could have seen this image when we talked about explainable AI. What is explainable AI? When we trying to debug our machine learning model and to understand how it answers our question. Then we saw the picture of different attention dots on our images, and we thought that if we train our model on white swan in the water, and then we'll show our model a dog, white dog, swimming in the water, our model will think that it's swan. Why? Because it's white and it's surrounded by water. So this is bias in our data set. And how to fight this bias? You should have people from different background and with good expertise. So basically experts in white swans, experts in black swan and different type of swans and different type of dogs. And they will validate your data set, trying to answer, is it correct data? And if you have a lot of bias in your data. Yep, another bias, you can Google it. Like if you ask Google for a picture of teacher, it's very often that Google will return you a picture of women. And if you gather this data and try to train your model to detect teachers, basically you will teach your model that all teachers are women. But and the same like with any other profession, very probably that firefighters will be associated with men and other profession. So this is bias in data, and we transfer this bias, our bias, to our machine learning model. And another problem which can arise when we gather data and then we train our machine learning model on the data is data leakage. And what does it mean? So it's very important step to split your data into chunks. The biggest chunk here, you can see, let's show laser pointer. Yeah. So you can see that 70% of our data goes to train data, and 15% to validation data, and 15% of test data. Yep. And our cat joined me. Do you see him? Yep. And what does it mean? That when you train your machine learning model, one moment, I will switch on laser pointer because it's worse. But so yeah, okay. So you train your model on trained data, and this is an iterative step. Like you train your model, you're trying to evaluate model on validation dataset. What is evaluation? It's basically measuring the quality of the model, accuracy of the model. And we'll talk about different evaluation technique in a while, in a second. But now let's try to understand this training process. And after we evaluate our model, we decide, is it our model good enough or no? And if not good, we repeat this process. We train, then evaluate, update, train. And if you are familiar with programming languages, this is for loop, so-called for loop, when you repeat the same actions over and over again. And one cycle here in machine learning world, it's called epoch. So you can have a lot of epochs. Like it's very common to have 100 or 1,000 or millions of epochs. Basically, you repeat this process of training, evaluation over for hundreds of times, and every in the end of every epoch, you answering the question if your model is good enough. And this is a very important concept here. So you train on trained data, but you ask the question about quality on validation data. So you see that you show a lot of examples to your model, like from trained data set, like this is cat, this is swan, this is dog, this is human, other animals, cars, and so on. And your model says, yes, I understood. So you have another part of images, and okay, if you understood, try to answer, is it cat or is it dog? And your model answers. And if the answer is good enough, you can end your training. But if it's not good enough, you repeat training. And you repeat not from the start, you repeat from the last checkpoint. Like your model, you will show in a few seconds how it works. But basically, after each epoch, you have some better performance on your model, some a little bit better. And when you reached your peak, like the model is good enough, and there is not reasonable ground to train further because it costs a lot of money, or you don't have enough data, or your model is good enough, or your model stuck on some plateau. You cannot reach a better number. So when you decide that training is over, only after that you go to test, and you're testing on some test data. And it's very important that this data is not seen during training. Why it's very important? Because if your model have seen this data during training, do you remember your model is very lazy? And if it's possible to remember all your examples, be sure your model will do it. It just will memorize all your pictures and will answer you. Is it cat? Yes, it's cat. I have seen this cat before. Is it dog? Yes, this is dog. I have seen this dog before. But when you push this model to production and you will show this model a new cat or a new dog, it will be complete disaster, because your model will say, I don't know what is this. I have never seen this picture. So in machine learning world, they call it overfitting. When your model is good on training, but is very bad in real world or on test example. And we call this model cannot generalize the knowledge enough. So the purpose of training model not remembering, memorizing all data, but to understand data. And if your model just remembers all data but doesn't understand it, it's a bad model and it will not work in production. How does it work in practice? So here we have code. We're using a very popular machine learning library, PyTorch, called simply Torch. One moment. Yeah. And here we split our data. So here we split to 90% for training, 5% for validation, and 5% to test. But it's not correct split. I just don't have enough data, so I decided to split like that. But rule of thumbs, it should be 70% to goes to training, and 15% should go to the validation, and 15 should go to testing. Just it's very popular, uh, but you can end up with any different number. You should decide on your own. But like if you have very few test and validation example, but a lot of training examples, you cannot be sure in your test, because you have very few tests in the end of the day. So, so here, sorry. Yeah. So here we splitted data and we loaded this data for training, and we just have a look on our data. We see a lot of dogs and cats, so there's small percentage of our data. We have our model. This model has some layers, and so today workshop is not about how to construct machine learning models, but in short, there are different layers in model, and different layers they are designed for different purpose. So if you're working with images, like in our example, it's very popular to use convolution layer and some normalization layers, and to put it all in sequential layers, like one by one. So your model basically goes from one layer through another, through another, through another, and each layer, it pays attention to different parts of your image, and then it tries to answer, is it dog or is it cat? But yeah, and in the end, you see, like you have these two numbers, cat, dog, but you start from some numbers like the size of your picture, like width of your picture and height of your picture, and 3 channels. So here are 3 channels, like blue, red, green of your image. Yep. And then you're doing some unit test on your model, just trying to answer, does it work or does it not? But it's not the question, does it work good? It just, does it work? And then you go to training. And here you can see that we train on train data. Yes. And then after we do a lot of training, well, not a lot of, but we go through each pictures, like all pictures what we have in train. And after we're done with training, we go to validation data set. And we measure quality of our model on each picture in validation data set. And after we measured quality of our model, we repeat. And here you see that we repeat for each epoch. And here is very important why we should not put our validation and test data set into training data, because we cannot answer then correctly, does our model works good on unseen data or not? Yep. So basically, this was data leakage. It's very important not to show your test data to your developers. So like when my developers ask me, show us your test data, and so we can understand why our model not performing good. I say, okay, I will show you the data, but don't use it for training, because you can cheat basically. If you show test data to training model, it will remember all those test examples, and your test would be always green, but your model would be garbage. Yep. And next problem is unbalanced data. And this means that you have a lot of examples of one thing and very few examples of another thing. And for example, here you can see that I asked generative AI to generate image of presidents of countries, and it came up with a lot of pictures of Trump. I don't know why, but there are mostly men and very few female. So very few women here, and it's very closely related to bias, yes. But here we have just like in bias, we don't have examples at all. But in unbalanced data, we have very few examples. And we can end up with the same problem that our lazy model, so let's say that we have 90% of men here and just 10% of women. And if we ask our model, is it man or is it women? Our model is lazy enough, again, and it will decide. So yes, if I say it's man, in 90% of all time, I will be true. So why I should learn 10% of women if I can give answer just man, 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 always man, and in 90% of all cases, I will be correct. So, and you will end up with this model that are always telling this is man, and this model, it doesn't pay attention, is it real man or women, or any other animal, cat, dog, or something like that. So, because this model will cheat you, this model will learn the easiest part to answer your question. So you always should pay attention to how many examples of each class you have in your data set. Yeah, so this was phase 1. And then we go to phase 2. So now we decided on our dataset, we answered a lot of questions. Do we have correct dataset? Do we have enough examples? Do we have bias in our dataset? Should we gather more examples of another class in our model? And let's say that we answered all yes on previous questions, and we are sure that our dataset is good enough. So we start training. And after we trained our model, we should answer, does our model work or not? And here we go to evaluation technique. And to answer the question of quality, we should learn about metrics. So we will look into our model. This model learns how to detect cats versus dogs. And very popular technique to decide on quality of models to look into positive and negative answers. And we can have true positives like TP, false positive, false negatives, and true negatives. What is true positives? Is when our model correctly decided and predicted class. So we ask our model, is it cat? And it says, yes, it's cat. And it's true, because on the picture, indeed, there is a cat. And what is true negative? So when we ask our model, is it cat? And we show an image of dog. And it says, no, it's not a cat, it's a dog. It's a true negative, because negative answer, no. And then we go to false. At first, false positive. If we show image of dog to our model and ask it, is it cat? And it says, yes, it's cat. So it says yes, positive, but for wrong answer, because we don't have cat on that image. And the same with false negative. When we show our model image of cat, basically, and we ask, is it cat? And it answered, no, it's not cat, but it's negative, false negative, because it's indeed cat. So bear with me if you get confused on it. We'll go to code a little while, and we'll see how it works. But at first, we will try to understand what we can grasp from those answers, like true negative, true positive. Why do we care? So when we measure a lot of true positive, true negative, so we can answer 4 very important metrics. So this is probably the most important metrics. We will talk about different metrics in the another slides, but this is like base of all quality testing of machine learning. This is accuracy, this is precision, this is recall, and one F1 score. Yep. So let's go to code, and we'll see how does it work. So here we have training. Yes, we stopped on our training. And we started our training, and our training gave us trained model. And you see that epoch 1, we had this accuracy 79%. And epoch 0, sorry. Epoch 1 is 78. So sometimes your model can be updated wrongly, and sometimes accuracy can go down. And you see that epoch 1 is even worse than epoch 0. So it's very important to pay attention to this process, and you should save the best model from all your epoch, not the last epoch, but from all your epochs. And you see that then we return to 79, and then we proceed to 80 during our training, and 81, 82, and so on, and we end up with 83. So, and you see that when we trained, we get this training accuracy, and at the same time, we gathered evaluation accuracy. And evaluation accuracy is very often lower than training accuracy. Why is that? Because during training, we show all training examples to the model, but we never show evaluation data. Yes, we already talked about it. And evaluation accuracy is a little bit lower because our model haven't seen this example. Haven't seen, sorry. And but it means that our model actually learning if the difference is not big enough. So basically 83 and 81 is not big difference. And then after we're done with all epochs, here we have 50 epochs. So we go to testing. And with testing, we test on test data here. And you see that with test accuracy, even lower than our evaluation accuracy. And this is also correct because in evaluation accuracy, we try and again and again with evaluation accuracy on each epoch. But on training, we just do it once after all training is done. So this is completely new data, but evaluation accuracy, we use this for deciding what the model should be saved. Yes. And when we decided on the best model with best evaluation accuracy, we go to testing, and the best model what works on evaluation dataset is not guaranteed that it will work on test dataset. But if your number is not very much different, you should answer that you have a good model because it gives the roughly the same number of accuracy on testing, evaluation, and training dataset. But if your model, like let's say, it would be 100% of training and 90% of on evaluation, but here only like 60% of accuracy, it means that your model is overfit and your model just memorized a lot of data before, but in the real world on test, it fails. And if you have here a big difference, you should go to your data scientists and developers and tell that we cannot push this model to production because it's bad. Yeah. And then, this is good when we measure this accuracy, but from my experience, I always trying to see the data, not just see some random accuracy, because I don't know what does mean accuracy 81. What is wrong with my model, and what should we do to have a better model? So I'm trying to use model and to see actually what where it failed. So, and I always have like different testing data sets. So here we have one test data set, but I have always a folder with images, and these images just only for, I call it testing after testing, but with like some verification from me that I understand why model fails. So here I use a model, and I am trying to go into my test, and I just gather all prediction, all truth, and then after I gathered all predictions, I am doing this confusion matrix. So this is confusion matrix, what we have seen in our slides here, with true positive, false positive. Yeah, and we built this with some Python library. It's called method of that library called confusion matrix. It's from scala-learn library, and it builds that table, and it basically tells this is in numbers. So from we predicted from test dataset, we predicted 527 cats as cats. So it's true positive, yes. And 115 cats were predicted like dogs. And 120 dogs were predicted like cats. And 488 dogs were predicted like dogs. So this is, if we answer a question, is it cat? So our dog versus dog would be true negative, cat versus cat would be true positive. This is true number, this is true number, this is false number and false number. And we can have a heat map. We divide it by 100, so we will see in percentage. So from our dataset, 42 examples were predicted correctly for cats, 39 for dogs, and we have around 9% error for cats and 9% for dogs. And here we go to this very important metrics. So we have accuracy, 81, but we don't know. It's not just one metric to decide about quality. Very important is precision. What is precision? Precision is we compare true predicted cats versus false positive. So basically, where we true positive is cats, indeed is cat, and false positives where we our model said this is a cat, but in true we have dogs. And recall is just a little bit different. We have true positives, cats versus cats, yes, cats, and they are indeed cats, but false negative that it was a cat, but our model says this is not a cat, this is false negative. And basically, F1 score, we just combine all those recall and precision metrics into one. And here we doing the same from code. We have precision like true positive divided by true positive and false positive. And we have number 81 and we have number 80 for dogs. If we're trying to answer the question, is it dog or not? And the same from recall, we divide it by true positive by plus false negative, and we have answer for cats and answer for dog, and then we have one F1 score. So basically, you can see that all our numbers are pretty the same, like 80-something%. It means that our model is balanced enough. So, but if we have one number is significantly bigger than another, we have unbalanced model. Sometimes model tells more like not cat, not cat, not everything, not cat, or everything is when we show cats or vice versa, like we show not cats, but it's saying yes, this is cat, this is cat. And if our precision and our recall is not in balance, we have another problem that our model is on very negative or very positive. And we should then go into our data, look why it works like that, and try to fix it. But in our example, it's not a problem because we have very balanced And so this is very important, like the most important metrics, and you can always pay attention to it when you testing your model. And then I already told you, then I tried to look into our problems, and I try to understand why it works not as expected. So here I just go to, through each incorrectly classified example, and not each, but I try to get a dozen of them, and to look why it doesn't work. So and then make it visible. So here you can see that maybe legs of human and two dogs got confused our model, or sometimes bad resolution. I don't know if it's visible for you, but those pictures are a little bit pixelated. So maybe bad resolution gave our model false impression. And so here you can see that this cat was classified as dog, probably of bad resolution, probably of some text here, and probably of because this cat, for me even, if not his face, it's very similar to some bulldog or something like that. Yep. So I'm trying to explain myself what's wrong with all those models, and because of lack of time, I will not repeat what we have seen in part 1. But when I have all those examples, incorrect examples identified, I am doing that explainable AI, what I have shown you in part 1, when we have those dots, and on that dot we see where our machine learning model pays attention and why it's identified wrongly. So here, yes, quickly, like this, you see these blue and red dots, and here you can see that why some examples were identified incorrectly. Yeah, but it was covered in previous parts, so I will not repeat it. Right. So moving on to our slides. Yes, and with cats and dogs, it's very funny, but you will say that nowadays cat and dog is old stories, old news, and we are impressed by ChatGPT, by some language models, and we would like to know how to test those models which work with text, not with cats and dogs. So again, for that purpose, we have metrics, and we have a lot of different metrics. And one of very important metrics is perplexity. And perplexity means that our model, basically each model which works with text, how does it work? It predicts some text. You give that model the start of sentences, and it predicts the end of this sentence. And perplexity just measures how good model with prediction. And if prediction have a bunch of random words, like here you see that we have a sentence, my cat is the best, and we ask a model to continue our sentence, and the bad model will predict something. My cat is the best car, my cat is the best animal, my cat is the best human, and a lot of different words. So to tell the truth, each model, even ChatGPT, it always has different sentences, different variation. Like it predicts a lot of words, but then clever algorithm. It pick up from all those predictions, like hundreds of thousands of predictions. It pick up the best matching words and to the end user we see only the best matching words. But behind the scene, ChatGPT predicts a lot of different words with different confidence. Like it has numbers. Like I think that 10% this is car, 20% this is animal, 50% this is a human, and 50%, 20% this is plane. Yeah, but good model will give us more better prediction. Like to my cat, it can be animal, it can be pet, it can be friend, and it's better model with better perplexity. So perplexity means just like a bunch of random words from language model, and good perplexity means that these words are not random, but they are contextually more connected to our sentence. So, and next is this is like at first this is very simple metrics, and when you measure the quality of your language model, you should always start with very easy metrics because it's easy to understand and it's easy to check. And after you're satisfied with easy metrics, you should go further with more complicated metrics. And here we have another just a little bit simple metric, and this metric just counts the number of matching words in what a language model gives us and what we expect. So here we expect that my cat is the best pet, and our model predicts my cat is a small animal. And basically, we just count, in simple metrics, we count how many words are matching. Like this is a very simple example, but in reality, this ROC matrix is a little bit smarter. It not predicts just words like equality of words, but it can understand that the same word can have different ending, and it can be put into different places of the sentences, and even if place in that sentence is correct or not incorrect, it will have some influence on your metric and your final score. But for simplicity, let's say that ROC just counts matching words. And if you have 4 matched from 6 total words, you have this number of perplexity. And the same with another simple metric like BLUE. It used very heavily in machine learning translation. And basically, it counts like this like a ROC. It counts the matching words, and it pays attention to order of that word's place in the sentence and is it correct form of the word. But BLUE used more with machine translation, and so here we'll see it from code. Like we have sentence in English, I have a cat, and we're trying to translate it to German language, and then we will count matching words. And so let's go to code. So here we have B. And we have evaluate library. This evaluate library has a lot of metrics built in, so we shouldn't write our own function to calculate any metrics. And we just can use it from evaluate library. And then we get our model. This model will translate from English to German. And and we have a small data set. Yes. So here we have English words and German. And like we cannot expect that our model will give us the exact translation. So it's very good to have some variation of possible answers. So like my name is Victor can be translated to my Name ist Victor or Ich heiße Victor in German. And the same, my mom is the most kindest person in the entire world can be translated either into this sentence or another sentence. And then we use our model here and we get translation. So this this model translates to meine Name ist Victor and meine Mutter ist die freundlichste Person auf der ganzen Welt. And it give us to answer to our English sentences. And here, like you cannot do exact testing like we used to API testing to web UI testing, because if we compare like very similar words like my name is Victor and my name is Victor but with dot, it would fail, yes, because there are two different strings. So even though we provided my name is Victor, my name is Victor without any punctuation mark at the end, it predicted my name is Victor with punctuation mark with dot in the end of the sentence. So any punctuation mark, any additional white space, it can ruin your test. So that's why we cannot use traditional ways of testing for our language models or any other AI solution. We should test it with metrics, not with exact comparison. And for that purpose, we use blue score, as we already seen on slide. So we get our prediction from translated text. Yes, here we have translated text from our machine learning model, and we have our reference what we expect from our machine learning model. So here prediction, yes, and here is our reference. And then we use a little bit smarter Sacre Bleu metrics, which pays attention not just to matching words, pairs of words, but to the position of that word, to correct form of that word, and so on. And we compute our score, and it gives 29, what is not bad, not good, like around 29 is just okay metric. You can read about blue score additionally, but rule of thumb that something below 20 is bad. From 20 to 40 is okay, and above 40 is good. And if you have above 60, probably you're doing something wrong, because even human cannot be so good in translation as you got from your metrics from your machine learning model. Yeah, the same with ROC. We use evaluation library to get ROC, and we compute our ROC. And you see that we have ROC1, ROC2. Basically, ROC1 just matches each word, one word. Yes, ROC1, one word, and it counts one word versus one word, and ROC2 it counts by pairs, like two words and then two words, then two words. And this is the difference between ROC and blue, because when we, let's say, blue we trying to match blue score by 2 words. It goes by let's say like these pairs. Like we have my name is Victor. So blue 2 with 2 pairs would go like my name, then name ist, then ist Victor. Like it uses 2 words, but it gets first word from previous pair. And rock is not using this previous word. It goes like my name and then ist Victor. This is the difference between rock and blue. Yeah, and so rock give us such examples, and rock score like 1 is the best ever, and if you have 1, it's probably you're doing something wrong because you cannot get the best ever matrix, never. And if it's close to 0, you have very bad machine learning model. Yep, and then let's go back to slides. So, and then we can use a little bit more smart machine learning metrics for language understanding. And those metrics, they not just count words and how and position of that words and form of that words. They pay attention to how good language model understands this word. And there are different evaluation technique. And it's good to combine them, like to test on different metrics, because sometimes your machine learning model can work good on one metric and badly on another metric. And there are just a few the most popular metrics, but you can find in internet a lot of different metrics more. And how does it work? So it I cannot run it on my laptop because those metrics they are very they demand very heavy computation power, and my laptop have no such power. But so I just copy paste a picture from Hugging Face. Hugging Face is very popular website dedicated to machine learning, and with a lot of training and a lot of different already prepared models and data sets. You can load machine learning model from Hugging Face and use it. And it's already trained. You don't need to train it on your machine, but you can just fine tune it to your specific problem. What is fine tuning is just you get a ready model and you just tune it a little bit on your small data set to work on your problem. But it's not today's topic. Yeah, and so how this one of the metrics is basically this is massive multitask language understanding here is shown. So here you ask LM a question. So here a question is glucose is transported into the muscle cell, and you give choices to your LLM, and it should answer it correctly. And you see that it gives you probability. Do you remember that I told you that even ChatGPT, it gives you not one answer, but basically a vocabulary with different answers. And so here we have probabilities for A, B, C, D, and you see that these models have highest probability to A, but correct answer is D. Sorry, I wrote correct answer is I, but it should be D. For example, I am not good in those glucose, so maybe I copy pasted something wrong. But so here you have A, and correct answer should be D. And so this is so your LM is wrong, and then you have a lot of those questions and like thousands of them, and then you measure performance of your machine learning LM on those all answers, and basically what you end up, you will have a lot of correct answer, a lot of wrong answers, and you will calculate your accuracy, your precision, your recall, your F1 score. And I already told you that even with the most sophisticated model, you will end up with the same basic accuracy, precision, recall. Yep. And there is another technique to test your LLM. Like you can test for faithfulness. Sorry, like this is you ask question, like wrong question to the model, and if the model gives you answer like yes, but it should say like I don't know. For example, you ask who is president of United States in year 3024, and your model will say that Lincoln is the president. This is wrong because it should say I don't know. So it's not faithful with you. It basically lies to you. And relevancy, is it a relevant answer or no? If you ask about capital of Ukraine and it gives you answer about some glucose, it's not relevant. And hallucination is basically if LM came up with some false fact, non-existent fact, sorry. And also you can check your model for toxicity. Does it use some vulgar, explicit language, and so on? And one more. So this is deep-eval library, and it can check for faithfulness, for toxicity, for any different questions and different metrics what we talked just right now. And back to our slide. And yes, so this is phase 2. Bear with me, we're almost done. So the end phase of our testing is push your model to production and look how good it works on production. And even the best model can end up poorly in production. Why it can happen? The first, because we communicate with client wrongly, and in fact, client provided us with pictures taken in one camera or with one data taken with one sensors, but on production we use different cameras, different sensors, different equipment. Some equipment is broken, some cameras has scratches on lenses, and sometimes our front end processes user data wrongly, so we store data distorted, like our client loads a picture of head, but because of wrong compression, we have wrong image in the pipeline, and we provide to our machine learning model some distorted image or some network problem that we just loaded half an image, and our model cannot decide correctly is it cat or dog, and so on. So there are a lot of problems, and we should all monitor those problems. So how to end up with good model in production? Just have a pipeline for monitoring all problems and log everything, and just pay attention to your logs. And if you see that your accuracy and precision recall of your model is degrading, just look into log if your equipment works as expected, if you don't have any network problems, and so on. And but those were like sudden degradation. Like in couple of hours or days, you see the problems with your model. But sometimes you can have some slow degradation. It's like slowly, day by day, percent of accuracy just decreasing, and half a year, 1 year, your model is complete garbage. And it's called like model decay. This degradation can be caused by such problems like data shift, model shift, concept shift. So data shifting means that your data is not correct anymore. So you during training, it was okay. Like when we predict what our customer will buy, they will buy sandals, flip-flops, or they will buy heavy boots. And during summer, our model was correct. It predicted that sandals would be hit of season. But during winter, this model is garbage because it predicts sandals, but people buying boots. Another is model shift, like because of some old data, model was good, but with time it degraded, and this was a problem with ChatGPT because it was limited to knowledge taken on September 2021. You couldn't ask him the ChatGPT question about some events which took place in 2022, 2023, and so on. So, and if the company behind ChatGPT would not, if they didn't update it, we would end up with very bad model, which shifted from its original value. And another problem is concept shift. And concept shift, that like your model is okay, it's up to date, but there's some new reality which you couldn't predict when you trained, like pandemic of COVID-19 and all people sitting at home, nobody working from offices, nobody walking, nobody traveling, and your model cannot predict correctly demand for like travel guides, some planes, some Airbnb booking, and so on. So basically, reality shifted, and your model has been left in the past. It lives in not existing reality anymore. Yeah. So that's all what I wanted to share with you. We have QR code to join us on cafeteria. Yeah, thank you very much.
Thank you very much, Victor, for this truly interesting session. Now I would like to switch to Q&A part of our event. But I want to note that if you guys watching this stream on VR community platform, I can see that there is no YouTube chat there. So you can switch to YouTube directly by clicking how to test AI solutions in the name, or just YouTube icon at the right bottom. And you can ask questions there in the chat. Right now we have one question. So could be the situation when we set more cats in our AI as learning data than it's needed. How we can understand that, and what type of test data can we use for this check?
So this is basically the problem which those metrics with recall and precision trying to answer. So precision trying to answer if we have false positive. So what is false positive again? That if our model says this is cat, but it's not a cat. So we have more cats than from our model that we have in reality. And the same with recall, like false negative, like we have real cats, but our model says it's not cats, it's not cat, it's so negative for cats, but in reality it's cat. So judging from that precision and recall, if we have like precision 80%, but recall 40%. It's like like clearly we have mismatch between positive and negative answers. So our model tends to prefer positive over negative answers. So basically, our model is cheating. It's trying to say positively on every question to reach better accuracy. But if we look into recall, we see that recall is false. So the recall is very low. It means that we could expect more negative than we got from our model. So basically, this precision and recall should answer this question if we have more cats. I hope that I answered it.
Thank you, Victor. Actually, the person who posted this question thanks you as well. Thank you for the lecture, it says. We have one more question. May you please name the tool you're using one more time? Thank you for your efforts. It was very interesting.
So for, okay, tools, like there are different tools, to be honest, and every day you can find more tools. And so for metrics, like simple metrics, there is sklearn. It's one of the oldest machine learning library, sklearn. And it has some metrics here from sklearn. Yep, you see my screen, yes?
Yeah.
Daria? Yeah, okay. Yeah, and you can import confusion metrics, you can import accuracy, recall, precision from sklearn. And if you go with language metrics, I prefer 𝐒𝐤𝐻. 𝐒𝐤𝐻 is library from Hugging Face, and once again, Hugging Face is a very popular website with different models, with different, like there are tons of materials you can read from Hugging Face, how to test models, how to test different models, what you should pay attention to when you're testing your model. It's not dedicated to testing, but they have a lot of testing materials. So 𝐒𝐤𝐻 is good to start from language understanding. And if you go with most like different metrics, there are some different libraries. The same you can find on Hugging Face. Some libraries you can use deep-eval. You can use OpenAI eval tool for here OpenAI evals to test your large language models. Basically, it uses ChatGPT behind the hood to access the quality of your models. And there is also Ragas library, Ragas test. Yeah, here for testing some Ragas is concept deeply connected with large language models as well. So once again, sklearn, eval, 𝐒𝐤𝐻, deep-eval, and then you should look into internet.
Thank you, Victor. I don't see any more questions in the chat, so I guess we can wrap up.
Yeah.
Thank you very much, everybody, again for attending this meeting. Thank you again, Victor, for this amazing presentation. Don't forget to join our cafeteria community to explore more interesting events. And we have actually one more question.
Okay.
The test strategy for AI. Any materials which may help?
So I would recommend to go back to part 1. I believe Sylvia provided some materials from TB tutorials, and I believe we had that strategy for AI testing in that part 1. Yeah.
You can watch the recording as well on our YouTube channel and find it on the VIA community. I guess that's it. So yeah, thank you again, everybody. Let's wrap up. Have a good day.
Thank you. Have a good day. Bye.